from the free body diagram, all we have externally is this distributed load, this linearly increasing distributed load. What do you get for the reactions at A, the pin, and B, the roller? Right, so you get B is 8 and A is 10 kip. So taking this, putting it over to the top of the VM diagram. Right, so we have a linearly increasing distributed load here. We have A and we have B, and that's all that's happening that's going to affect V. We're going to see that this is going to make it more complicated to be able to solve, especially when we get to the M step, because we're starting with a first order line. So in the V diagram, this will be a second order line looking forward. But first, we start at 0, and we're going to jump up by 10 to 10. And then we have the tricky part here. Between these two lines, we're going to drop by 18, which means we're going to drop to -8. However, the distributed load here is linearly increasing. So as we saw before with how do we determine the concavity of M based on the first order line in V, it's the same idea here. The concavity of V is determined by the value of the intensity at that point. So over here, the intensity of the load is 0, which means that the slope of V is 0. Whereas over here, the intensity of the load is a -3 since it points down. A -3 kips per feet. So by the time we get over here, our slope becomes becomes -3. Okay, so this is first order. This will be a second order line connecting it. And that's, again, how do we determine the concavity of that line. Starts at 0, and the slope ends at a -3. I'm sorry, yeah, the slope ends at -3. Okay. On the line, there's no point loads, so it does not have a jump. Between the line, there's no more distributed load, so it stays at -8. And on the last line, we have a point load up, so it jumps up by +8 to 0. So we get back to 0. So making the V diagram wasn't terribly difficult because it's similar to making the M diagrams we saw before. But now using the information we need for the M diagram is going to be trickier because we have to know what is the value below the V graph at all of these points. So first of all, there's a 0 crossing, which will influence the M diagram. So we need to know what's the value under this part of the graph, under this part of the graph. And then the easy part here where it's rectangular, it'll be -8 times 6 is -48. So that's the one easy piece here. So first thing we need to do is how are we going to find where does V go to intersect the graph at 0? So how far do we need to go from the 10 down to the 0? So we know for this distributed load, the triangle has a total area of 18. So we need to find when that area, we have to go from 10 down to 0. So the value of V had to go down by 10. So we need to know where is the area of the triangle, only 10, and that'll tell us how far it took to go from 10 down to 0. So it's basically the same as that integration argument. We need to integrate the triangle until the area is equal to 10, or -10 in this case, because at that point, our V diagram would have lost 10, which meant that it went to 0. So the total area is 18. We just want to find the amount of the triangle that has an area of 10. The whole triangle has a length of 12. So we need to find this length of x. So what was the relationship we used last week to find, based on similar triangles, how can we find x in this equation? Or make an equation to find x.
Is the ratio to the sides versus the ratio of the area to the square?
Right? We can use the similar triangle relationship where often the way we used it in the past is that the ratio of the sides are, say, the ratio of the legs on the horizontal are equal to the ratio of the legs in the vertical. It's a similar argument for areas of similar triangles. However, this relationship is squared. And then if we're looking at volumes, it would be cubed for similar triangles or similar triangular solids. Right, so the ratio squared of the sides is equal to the ratio of the areas. So that means that we have to go to the right, that x is going to equal 8.94, approximately. Again, what does that mean? If we had a triangle, or the piece of the triangle that was 8.94 feet long, and we found the area under it, we would have found that that is negative 10, which means the value of v would have dropped by negative 10, which takes us to v equaling 0. And that's the point of what we're doing here, is to find how far it takes to drop to 0. And then the remaining is just going to be 12 minus the 8.94, or about 3.06. And we need to find where that zero crossing is because on the M diagram, first of all, we need to know how much of this area is positive, how much is negative, and we need to know where that maximum is going to occur in the M diagram. We need to find the area under these parabolas, these second-order curves we have here. If you go to the equation sheet that you were given, there should be pictures for the moments of inertia and how you find areas of parabolas in there. And there's two different kinds of parabolas. There's concave and convex parabolas. So you need to make sure you're using the correct equation for which one we're dealing with here. So for this one, where the concavity looks like that, what's the area it says to calculate that, the area under that sort of parabola? Right, so for the parabolas that are bulging out like that, it's going to be 2/3 the base times the height. Right, so that's why it was important to find the base here of 8.94. And the height of this parabola is 10. So 2/3 10 times 8.94. We get approximately, there will be some rounding in this one, but it has an area of about 59.6. However, this other piece here has the opposite concavity. It's bulging inward. So we have to make sure, again, we're using the correct equation to find its area. So what was the equation for one that bulges inward? Right, so again, depending on the concavity, we have to use this area, the 2/3, or the 1/3, depending on it. Since this one bulges in, it's going to be 1/3 times the 3.06 times, in this case, the negative 8. So you should have negative 8.16. All right, so the value of M we're now ready for since we have all the areas under our shapes. At the left-hand side, there's no couple, so there's no jump in the value of M. But between the lines, we're going to go up by 59.6. However, now that we're integrating, this is a second-order curve. This is going to be a third-order curve in M. So potentially, it could have like an inflection point. We don't necessarily know quite what the shape looks like. And this is where, again, remember, it's just a sketch we're after here. We're going to get an approximation of what it looks like. Now, for second order, it's not too bad to assume, okay, we can at least get the concavity of it. For M, we're going to use basically the same technique and assume that there's not going to be an inflection point. Or really, we don't have to assume that because we can look all the way to have an inflection point. The second derivative would have to be equal to 0. So in this case, because the second derivative is not equal to 0, since the loading is the second derivative of M, there will not be an inflection point. So we can treat it like similar to how we did second order curves. So here, the slope of the M curve is going to start at 10. And then by here, the slope is going to be 0. So it looks similar to what we did for the second order curve, but it is technically a third order curve if we went into the underlying math here. All right, so on the line, we're at 59.6. There's no couple here. By the time we get to the next line, we're going to lose 8.6. Again, this is an estimate, and it's going to be slightly off by the end, but thank you. So we're going to drop by 8.6 down to 51. Again, based on the concavity, it's going to start with a slope of 0, and it's going to end with a slope of -8. The last piece, we're at 51. We dropped by 48, but because of the kind of assumption we made here about using the area, in this case, we don't exactly get back down to 0. So for this one, again, it's just a sketch. We can fake it that we do get back to 0. If you're coming out with a large number difference, like 30 or 40, then you most likely did something wrong. If you're getting just a small discrepancy there, a couple percent, then it's either due to a possible rounding error, or not a rounding error, but a round off that you made since you're only keeping 2 digits. Or like here, we made the assumption for the area here wasn't quite right, but it's close enough for this problem. Because really, this was right, and this is the most important part anyway, that we reached that maximum of 59.6. These intermediary parts don't matter for our purposes as much, because the maximum we did predict correctly. The rest of this curve was okay. So the maximum, the most important feature, 59.6, is right. And then down here, we found that the maximum value of V was equal to 10.